Good afternoon, everyone. I'm Jiang Feibo, an associate professor from Hunan Normal University, China. It's a great pleasure to present our recent work titled Bridging Semantic Communication and Large AI Models, a new paradigm for intelligent communication. In this talk, I will introduce how we integrate large AI models into semantic communication systems to achieve intelligent, task-adaptive, and highly efficient information transmission. To lay the foundation for this discussion, let's first revisit the three levels of communication proposed by Shannon and Weaver. At the technical level, the focus is on accurate and efficient transmission, addressing noise and interference through techniques like error correction and channel estimation. The semantic level goes further, ensuring that the meaning of the message is preserved and correctly interpreted by the receiver. This includes semantic encoding and decoding, supported by knowledge bases. At the highest layer, the effective layer, communication aims to achieve a desired impact, such as influencing decisions. These three levels form a systematic framework for designing next-generation communication systems. Then, we can provide an overview of the key components of a semantic communication system, which aims to transmit meaning rather than just raw data. First, we have the semantic encoder, which extracts meaningful information from the input data and converts it into a compressed semantic representation. This reduces the data size, ensuring efficient transmission. Next, the channel encoder steps in, applying modulation and error correction to ensure robustness against noise and interference during transmission. On the receiving side, the channel decoder demodulates the signal to recover the semantic representation. The semantic decoder then reconstructs the initial information using the received semantics. Its role is important in ensuring the meaning is accurately understood. Supporting these processes is the knowledge base, which provides related contextual and technical knowledge. By using this shared knowledge, both the encoder and decoder improve their understanding and decision-making, further enhancing communication accuracy. The emergence of NUMs marks an important turning point in this timeline. Let me now introduce what NUMs are and how they are classified. NUMs are neural network models containing hundreds of billions or even trillions of parameters, giving them powerful abilities to understand and process information. The development of NUMs has sped up our progress towards AGI. These models are divided into several types. First, we have large language models like GPT, NUM, and ChatGLM, which excel in understanding and generating human language. Next are the large vision models such as SIM, DALL-E, and Dino, which specialize in visual recognition and generation. Moving beyond the single type of input, large multimodal models like GPT-4 and Gemini Pro combine text, image, and video understanding for rich interactions. We also have word models like Sora, designed to simulate environments and predict future actions, commonly used in video generation. Finally, large reasoning models such as OpenAI O1 and DeepSeek R1 improve the AI reasoning and decision making. Beyond their capabilities, NUMs also take on particular roles in semantic communication systems. Let's explore those in more detail. First, as data generators, NUMs can produce synthetic semantic data, such as CSI labels or structured inputs for semantic tasks, enabling model training without the need for real-world data. Second, they act as knowledge organizers by extracting semantic representations from raw inputs and use intents. This supports the construction of knowledge bases, enhancing the accuracy and robustness of semantic encoding. Third, as task schedulers, NUMs can coordinate semantic communication workflows across multiple users and agents. They dynamically assign encoding and decoding responsibilities based on the communication task requirements. Finally, NUMs serve as system designers capable of interpreting natural language specifications to construct semantic communication architectures. They can auto-generate core components such as semantic and channel encoders, supporting the rapid deployment of intelligent semantic communication systems. Together, these capabilities make NUMs powerful enablers of next-generation semantic communication. Building on this role, we now consider how NUMs empower each stage of an end-to-end semantic communication pipeline. At the same side, NUMs perform semantic extraction using their vast knowledge and multimodal capabilities. Through advanced processing, they extract meaningful features from the input data, reducing unnecessary information and optimizing bandwidth usage. On the receive end, NUMs contribute to semantic reconstruction by rebuilding the initial message. Even in the presence of noise or data loss, NUMs ensure accuracy and context-aware communication. Additionally, the integration of knowledge bases allows NUMs to further enhance communication effectiveness. With access to both private knowledge for personalized understanding and public knowledge for shared context, NUMs adaptively interpret and generate accurate responses. Furthermore, NUMs also support channel estimation. By analyzing channel conditions in real time, they can predict and reduce communication issues, ensuring stable data transmission. Let's now look at how NUMs support goal- and task-oriented semantic communication systems. Unlike traditional end-to-end semantic communication methods, these systems focus on task usefulness rather than just data transmission. At the same side, NUMs perform goal-oriented semantic recognition and filtering. By understanding the purpose of communication, they extract and transmit only the most related information, reducing bandwidth usage. Goal-oriented knowledge bases are maintained by both the sender and receiver, ensuring personalized and task-aware communication. During the transmission, NUMs handle semantic understanding and correction by knowledge bases. Through their advanced reasoning capabilities, they identify and correct semantic noise, ensuring accurate message transmission. On the receive side, NUMs enable goal-oriented semantic reconstruction. they interpret received data within the context of the intended task, ensuring the receiver understands the message as intended. Furthermore, the joint NUM semantic channel coding framework enables at the same time optimization of the non-prompt semantic representation and channel-level signal encoding, thereby improving overall transmission efficiency and stability. Expanding further, let's take a closer look at how NUMs empower semantic communication systems across multiple dimensions. First, in multimodal semantic communication, NUMs use their ability to integrate information from various sources like text, images, and videos. By performing cross-mode alignment, they create unified semantic representations that enhance the accuracy of semantic extraction. Second, we see important advance in multitask semantic communication. NUMs can handle diverse tasks concurrently using task instruction fine-tuning. This improves flexibility to new tasks with minimal retraining. Lastly, in multi-user semantic communication, NUMs optimize resource allocation through semantic cell remodel. By transmitting public semantic information efficiently while ensuring personalized data, the overall bandwidth consumption is reduced. Then, I will introduce the large AI model-based semantic communication framework, or NUM-SC for short, in which we use same model in this image semantic communication. The major challenges for knowledge bases include limited knowledge representation, frequent knowledge update, and insecure knowledge sharing. To address this, NUM-SC introduces several innovations. First, SIM is used for high-quality semantic segmentation. Next, the attention-based semantic integration method accurately integrates these segments, enhancing segmentic awareness. Finally, the adaptive semantic compression compresses the data efficiently, reducing overhead and ensuring fast transmission. The core strength of NUM-SC is knowledge base. So why NUMs ideal for semantic communication? Let's look at their knowledge handling abilities. NUMs are pre-trained on large datasets, enabling them to store and understand vast amount of prior and background knowledge. This makes them reliable for semantic extraction, reasoning, and decision-making. A key advantage of using NUMs as knowledge bases is their accurate representation of knowledge. With trillions of parameters, they capture complex relationships and provide strong semantic understanding. Another benefit is their low cost and secure knowledge update. Methods like prompt tuning and fine-tuning allow quick and resource-efficient updates without their need for frequent retraining. For different input types, we have specialized NUM-based knowledge bases. For example, GPT-based knowledge bases for text-based communication, SIM-based knowledge bases for image-based communication, and Wave LM-based knowledge bases for audio-based communication. Now, let's dive deeper into the inner workings of the LAM-SC system and see how these components work together to enable end-to-end semantic transmission and reconstruction. We begin with semantic segmentation, where a SKB identifies and separates all objects in the image without prior training. Next, ASI mimics human perception using channel and spatial attention to select related objects. These are merged into a semantic aware image. This image is encoded by a CNN-based semantic encoder, followed by an adaptive masking component that removes redundant features. And the receiver, the channel decoder, and the semantic decoder reconstruct the image, and the same based knowledge basis is applied again for objective recognition. There are the experiment results reported in this paper. In the context of NAMS-empowered multimodal semantic communication, or LAM-MSC for short, we face several key challenges, including data heterogeneity, semantic ambiguity, and signal distortion. To address this, we propose several groundbreaking solutions. MLM-based multimodal alignment uses NAMs like Cody to transform multimodal data into a consistent text format, preserving semantic meaning. Personalized semantic understanding is enhanced through a GPT-based knowledge base, helping reduce ambiguities in personalized communication. Lastly, generative channel estimation uses CGAN to reduce the effects of fading channels, improving the stability of semantic transmission. Let's take a closer look at how GPT-4 functions as both global and personalized knowledge base in semantic communication systems. First, GPT-4 acts as a global knowledge base shared by all users. With its large scan parameters and multi-head attention models, it performs very well in semantic extraction and recovery. Additionally, GPT-4's pre-training on diverse datasets allows it to store rich prior and background knowledge, providing robust generalization across different fields. For personalization, while measures like adaptive training and LoRa can frighten GPT-4, these approaches require advanced skills and a large amount of computing resources. Instead, prompt tuning offers a more accessible solution. Users can create a personalized prompt library containing information such as their language, identity, and performances. By inputting this prompt with text data into GPT-4, users receive customized semantic outputs without modifying the model itself. Now that we've introduced GPT-4's role, let's walk through the semantic communication workflow powered by the NAMs. From transmission to reconstruction, we start with MMA-based model conversation. For multimodal data, MMA converts them into unified text, preserving semantic alignment across modalities, making the system process meaning consistent. Next, LKB-based semantic extraction extracts only essential personalized content aligned with the sender's intent. Redundant information is discarded, reducing transmission node while keeping communication effective. The third stage is CGE-assisted semantic transmission. The semantic encode converts content into compact features. Use CGAN, we estimate channel state information to help the channel decoder recover data despite noise. The semantic decoder then reconstructs the semantics from the received signal. During the semantic recovery, the receiver applies its own LKB to interpret the message, ensuring accurate understanding aligned with its context. Finally, MMA-based model recovery converts the text back into its initial form, maintaining initial meaning and accuracy. These are the experiment results reported in this paper. Switching gears to cross-modal semantic communication, we now present visual language model-based cross-modal semantic communication systems, or VLM-CSC for short, which addresses several key challenges in cross-modal semantic communication. First, traditional semantic communication systems struggle with low information density. Second, the issue of catastrophic forgetting arises in dynamic environments. Finally, traditional systems cannot handle varying SNR. To address these challenges, we introduced the cross-modal knowledge base using a visual language model, BLIP, to extract high-level semantic text from images, thereby removing information density. Furthermore, we use stable diffusion to reconstruct images from the extracted semantic text, ensuring faithful visual recovery and preserving semantic consistency. We also propose memory-assisted encoder and decoder, which use short and long-term memory tools for continual learning. Lastly, the noisy attention components dynamically adjusts semantic and channel encoding based on the SNR, ensuring robustness in varying SNR conditions. Let's now follow the complete processing pipeline of VLM-CSC to see how each component contributes to efficient cross-modal semantic transmission and recovery. First, the transmitter employs BLIP to convert images into high-density textual descriptions. This not only reduces the bandwidth requirements, but also ensures the essential semantic contents is captured. This not only reduces the bandwidth requirements, but also ensures the essential semantic contents is captured. Next, the text data is processed using a semantic encoder and a channel encoder. The integration of noise attention components dynamically optimizes the encoding based on the current channel conditions, ensuring robust communication. Once transmitted, the data is decoded using the channel decoder and semantic decoder. The system then applies stable diffusion to reconstruct the initial images using the recovered text. The memory-assisted encoder and decoder employs a memory structure, ensuring the system remains knowledge across different environments. In addition to the core pipeline, MED and NAM play essential roles in ensuring flexibility and robustness across dynamic environments. MED uses a dual memory design. The short-term memory stores recent data samples, while the long-term memory preserves important knowledge from the previous experience. When the short-term memory reaches its limit, related data is transformed to the long-term memory, ensuring both adaptive learning and memory keeping. On the other hand, NIM is responsible for enhancing system robustness through SNR-well adjustments. It dynamically distributes resources between the semantic and channel encoders based on real-time SNR conditions. For no SNR values, MAN gives more importance to channel encoding to maintain stable communication. In contrast, for high SNR values, more emphasis is placed on semantic encoding to ensure semantic accuracy. There are the experimental results reported in this paper. Moving into the 3D space, we introduce the challenges and contributions of the generative AI mode assisted 3D semantic communication, or GAM 3D-SC for short. This system faces three main challenges, includes 3D semantic extraction, latent semantic redundancy, and uncertain channel estimation. To address these challenges, GAM 3D-SC introduces three key solutions. For semantic extraction, it first employs the SEM to generate multi-view images of the selected standard object, capturing diverse semantic views. These images are then used by NERF to reconstruct the full 3D scene. Last, the adaptive semantic compression model uses a dual-head encoder to reduce redundancy, greatly lowering communication costs. Finally, GDCE, a hybrid approach of CGAN and diffusion model, ensures precise channel state information estimation. Let's now look into the detailed workflow of GAM 3D-SC to understand how its components handle 3D extraction, compression, and transmission. The process begins with 3D-SE. Here, the SEM selects the key 3D objects based on user inputs. These multi-view images act as a semantic representation of the original scene. Next, the ASCM applies a dual-head encoder to transform the images into semantic data, removing redundant information and reducing communication costs to ensure robust channel transmission. The GDCE method uses a CGAN to estimate the channel state information, and a diffusion model further refines the estimation for accurate signal recovery. Finally, the receiver employs NERF to render the objects from multi-view images and reconstruct the 3D scene. Of course, effective communication also depends on accurate channel estimation. Let's look at how GDCE enhances this critical step. The workflow begins with CGAN-based channel estimation, where a CGAN is used to estimate channel state information. Next, the diffusion model refines the estimated CSI. The diffusion model works through a forward-backward denoising process, which improves the quality of the channel information. These are the experimental results reported in this paper. Now, let's look at how NUMs contribute to token phase-based semantic communication. We present the large generative model assisted token phase semantic communication system, or LGM-TSC for short. This system addresses several challenges in token phase video communication, including low bandwidth utilization, semantic ambiguity, and diminished QoE. The LGM-TSC system uses a generative semantic extractor that converts video into text, greatly reducing bandwidth. An LLM-based knowledge base resolves semantic ambiguity and ensures accurate data transmission. Finally, a generative semantic reconstructor reconstructs the video at the receiver, use advanced generative models like BERT-with-2 and SetTalk, maintaining high QoE for users. Let's now walk through the full system workflow, starting from the send side. First, GIC is performed using the FunSR model, which converts talking face video into text, thereby reducing bandwidth consumption while preserving key semantic content. Next, a private knowledge base at the transmitter, supported by large language models, ensures accurate semantic extraction by resolving ambiguities and adapting the textual information according to current SNR conditions. Meanwhile, a public knowledge base maintains user-related data, such as facial images and vocal features, which are essential for reconstructing a high-quality video at the receiver side. Following this, the system proceeds with encoding and transmission, while the semantic encoder and channel encoder collaboratively process the text for efficient sending over the communication channel. Finally, at the receive side, GSR is carried out. The BERT-with-2 model reconstructs audio, and SetTalk generates a high-accuracy talking face video, ensuring that the speaker's real intent, expression, and vocal timbre are faithfully preserved. To improve robustness in wireless environments, we propose a joint knowledge-based semantic channel coding method. Since LLMs are hard to integrate directly due to their scan, we design a prompt encoder that controls LLM outputs, allows it to indirectly take part in encoding. This system unifies prompt, semantic, and channel encoder and decoders into a coordinate framework. Each component is trained with a distinct loss function, mutual information for channel coding, cross entropy for semantic encoding, and cosine similarities for prompt optimization. We developed a prompt encoder based on a fuzzy inference system. The input of the fuzzy inference system is the SNR value of the channel, and the fuzzy semantic set is high, middle, low, which corresponds to the prompt encoding rules, while SNR is different. When the SNR is high, the prompt encoder directs the LLM to produce more accurate text content. Conversely, when the SNR is low, the prompt encoder instructs the LLM to compress the output text while maintaining semantic meaning. In this example, the length in fuzzy rules means the output length of LLM. There are the experimental results reported in the paper. Now let's look at how NUMs contribute to multi-user semantic communication. We present the lightweight vision mode-based multi-user semantic communication system, or LVM-MSC for short. The LVM-MSC system addresses challenges in current image semantic communication systems. First, traditional NUM-assisted knowledge bases are too large and slow for real-time edge deployment. Our lightweight knowledge base, built on FastSim, greatly reduces parameters and inference time, making it age-friendly. Second, semantic encoders often ignore pixel-level redundancy, leading to unnecessary bandwidth consumption. We introduce the efficient semantic encoder and decoder, which performs both picture and semantic compression, use adaptive masking and MAE. Third, current system overlook semantic similarities across users. We design a multi-user semantic steering component that extracts shared semantics and transmits them once for all users, greatly cutting redundant data. We illustrate the workflow of our LVM MSC semantic communication system. It starts with the net weight knowledge base, which uses FastSem to extract essential semantic objects from the input image, greatly reducing computational load. Next, the ESC uses MAE and adaptive masking to compress both semantic and picture-level redundancy, improving transmission efficiency. The multi-user semantic steering component then analyzes the semantic needs by all users, extracts the shared parts, and broadcasts them once, minimize redundant transmission. The channel encoder-decoder measures semantic features for wireless transmission and recovers them at the receiver. Finally, each user reconstructs the image by combining shared semantics with their personalized semantic features, ensuring efficient and accurate recovery. This design greatly improves bandwidth efficiency, scalability, and semantic accuracy in multi-user scenes. In our system, the lightweight knowledge base plays a key role by identifying and labeling key semantic objects in an image. This is done using FastSem, which replaces heavy VIT backbones with lightweight CNNs, achieving a 10 times reducing in parameters and 15 times faster inference. Next, the ESC uses a MAE to transform the image into embeddings and extracts high-level semantic features. An adaptive mask generator then selects only the important regions and discards redundant or background areas. This approach enables joint compression at the pixel and semantic levels, greatly improving bandwidth efficiency while preserving meaning. These are the experimental results reported in this paper. Extending to more complex settings, M4SC supports multimodal, multitask, and multi-user scenes. M4SC addresses three challenges as follows. First, semantic mismatch across modalities leads to difference in representation and understanding. To solve this, M4SC employs a CAM-based cross-modal alignment component, which decomposes visual features and aligns them with language semantics, enabling unified interpretation across modalities. Second, multitask learning often suffers from semantic overlap and interference, causing reduced performance. M4SC introduces an instruction-based tuning approach, using neutral language prompts to guide task-based learning. Third, redundant semantic transmission in multi-user scenes increases bandwidth usage. M4SC integrates a semantic sharing method that separates shared and private semantics. Shared content is transmitted only once to all users, while private semantics are transmitted separately. Let's now examine the design and capabilities of our tailored MLLM for semantic communication. First, MLLMs enable high precision multimodal alignment. Second, they offer strong generalization in multitask settings. Third, they enhance multi-user transmission efficiency. Now, let me explain the tailored MLLM structure. The Vision Semantic Encoder uses a pre-trained SIGLIP VIT model. The cross-model semantic projector uses a CAN to map visual embeddings into the LLM's semantic space. The LLM-based semantic encoder integrates the transformer visual features with text inputs using a transformer decoder. Finally, the LLM-based semantic decoder uses a softmax layer to generate semantic outputs. The semantic encoder and decoder are built on Gemma 2 2B. Together, these components make the tailored MLLM highly suitable for multimodal and multitask semantic communication. This example demonstrates the full workflow of M4SC. At the base station, two users request different text. One performs image captioning, the other visual question answering. Both provide image and text inputs. These inputs are processed by a multimodal encoder. Next, the LLM-based semantic encoder generates deep semantic representations. A semantic comparator then analyzes the two users' semantic content and separates it into public semantics, for example, the shared object Jerry, and private semantics, for example, yellow duck for user 1 and female mouse for user 2. The semantics are encoded once and transmitted via a shared channel, while private semantics are sent through encoders for each user. At the receiver side, each user recognizes the public and private semantic content, decodes it, and uses the LLM-based semantic decoder to complete their respective tasks. There are the experimental results reported in this paper. In 6G communications, large language models face 4 major challenges: untimely technical data, lack of communication knowledge, insufficient logic reasoning, inadequate evaluation and refinement. To address these challenges, we propose ConLLM, a multi-agent system enhanced by LLMs and enhanced components. The multi-agent data retrieval component retrieves and summarizes 6G knowledge from private sources. Then multi-agent collaborative planning component decomposes complex tasks and generates multiple feasible solutions using planning agent. Finally, multi-agent evaluation and reflection comments continuously assesses and improves these solutions through multi-level memory and self-checking feedback. By integrating LLMs with key agent system components, such as retrieving planning, tool usage, memory, evaluation, and reflection. Their usefulness and effectiveness in 6G communication scenes can be substantially enhanced. First, the MDR component searches communication knowledge from outside data sources in natural language according to user requirements. This process involves collaboration among multiple specialized agents, including a security agent, a condensant agent, and an inference agent. Once the related communication knowledge and task specifications are obtained, they are passed to the MCP component. MCP uses multiple planning agents and constructs a chain of subtasks to derive a solution based on the retrieved knowledge and task objectives. With the assistance of various tools, it solves each subtask and produces an initial result. Subsequently, the MER component introduces an evaluation agent to assess the final outputs of each subtask chain and assign rewards. In addition, it employs a reflection agent and a refinement agent to generate optimization suggestions. Finally, these suggestions are sent back to the MCP component, guiding it to replan and generate improved sub-task chains and results. Through this iterative process, the system reaches an optimal solution, which is then sent to the user in natural language. There are the experimental results reported in this paper. Here is the complete architecture of our prototype, showing how data flows through the system. The initial video is first processed through a speech recognition component, after which the transcribed text is passed into a large language model knowledge base for semantic extraction and disambiguation. The resulting semantic representation is then encoded using a semantic encoder and a channel encoder deployed NVIDIA Jetson embedded board. The encoded data is transmitted over a wireless channel to the receiver by a 5G component. At the receiving end, channel decoding and semantic decoding are performed to recover the semantic content. The reconstructed text semantics are then converted into speech through a speech generation component, which preserves the initial speaker's timbre features. Finally, a visual language model combined with extracted facial features is employed to reconstruct the video and generate a realistic talking face output. That's all. Thank you.